This real-time fluid dynamics simulation was created entirely in Julia.
Wow.
You can create this animation in the comfort of your own home and on your own computer with just a few lines of code. How, you may ask? Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. This video is the final episode in the scientific computing series. We covered a lot of heavy subjects during the past 12 episodes, so I thought that we should end the series with something fun. In my opinion, one of the coolest presentations from JuliaCon 2021 was this video, made by Gabriel Weymouth, where he introduced his package, Waterlily.jl. According to its GitHub page, Waterlily.jl is a simple and fast fluid simulator written in pure Julia. Waterlily.jl is an experimental project, and its GitHub page contains a couple of really cool animations. If you enjoyed these animations, and if, by the end of this video, you enjoy using the Waterlily.jl package, then please consider going to the GitHub page, and please consider leaving a star. In addition to these animations, the GitHub repository also contains several example files that you can use to create both two-dimensional and three-dimensional fluid simulations. One of those examples is for something called a three-dimensional Taylor-Green Vortex. This is the example that I'll be using for today's demonstration. I updated the code to work with the latest version of GLMakie, and I made a few modifications to make the animation longer and slower so we can get a better view of what's going on in the simulation. Before we get to the code, let's get a quick lesson on fluid dynamics. Fluid dynamics describes the flow of fluids, which includes liquids, gases, and plasmas. Fluid dynamics is a subdiscipline of fluid mechanics, which is a subdiscipline of physics. Fluid dynamics has been applied to both science and engineering in fields such as aeronautics, chemical engineering, meteorology, astrophysics, and many other subjects. Some well-known equations from fluid dynamics are the Navier-Stokes equations, which are partial differential equations that describe the motion of fluids. One application of the Navier-Stokes equations is the Taylor-Green vortex. Imagine that you have an enclosed space filled with a fluid, either a liquid, a gas, or a plasma. That fluid starts at rest, but then you introduce a quick burst of turbulence by creating a vortex. And then you stop to watch what happens. The vortex will initially churn up the fluid very quickly, but that vortex won't last forever. The vortex will dissipate over time, so the fluid will eventually return to its equilibrium state. The Taylor-Green vortex is a mathematical model that describes how that vortex decays over time. We can animate a Taylor-Green vortex in Julia by using a combination of the GLMakie.jl planning package and the Waterlily.jl package. We'll start by creating a file that defines the function that will record an animation of the simulation. And then we'll combine it with a file that defines the Taylor-Green vortex simulation function. But before we do all of that, let's begin with some setup work. For this demonstration, I'll be using VS Code. Waterlily.jl takes advantage of multi-threading. So before writing any code, be sure that you have the correct number of threads for your computer set up in VS Code. As a reminder, you can set the number of threads in VS Code by going into Settings and searching for Threads. Under Julia Num Threads, click on the link and update the number of threads in the settings.json file. If you have a Julia session open, you will need to close out of it before updating the number of threads. If you're interested in learning more about multithreading in Julia, be sure to check out episode 803. With that said, let's get started. In the Explorer panel, create a new folder for this tutorial. Start a new Julia session by using Alt-J, then Alt-O. Change your present working directory to the tutorial directory that you just created. Enter the package manager by hitting the closing square bracket. Activate your tutorial directory. Add the GLMakie package and the Waterlily package. Exit the package manager by hitting backspace. Okay, let's write the code to record the simulation. In your tutorial folder, create a new file named recordvolume.jl. This file will contain the code for a single function that will generate the animation using GLMakie. This file will be called by a separate file that we'll create in the next section. So all we need to do is enter in this code and then save the file. The first part of this function is standard Makie code. Makie offers several different themes to choose from. You can select any theme that you like. Also, you can choose any resolution that you like. The higher the resolution, the sharper the animation. But the trade-off is that it'll take longer to generate, and the file size will be larger. Makie offers several different rendering algorithms to choose from as well. Depending on what you're looking for, you may want to select a different algorithm. Please refer to the Makie documentation for more details about these options. The next part of this function is incorporating Waterlily code with a GLMakie code. For example, the sim_time function and the sim_step_bank function are from Waterlily. Be sure to save this file. Okay, so that does it for this recording code. Let's move on to the Taylor Green Vortex code. In your tutorial folder, create a new file named Waterlily_demo.jl. For this file, we're just going to enter in this code, and then we'll execute the entire file when we get to the end. Let's start by loading the Waterlily package, along with the code from the file that we just created. Next, we need to define the Taylor Green Vortex simulation function. For the function parameters, P stands for pressure, and RE stands for the Reynolds number. This code comes directly from the Waterlily GitHub repository, and I have to confess that I don't fully understand the math used in this function. But one thing to be aware of when typing in this code is that Waterlily uses a lot of Unicode characters for Greek letters. For example, this is the lowercase Greek letter nu, and not the lowercase ASCII character or the letter V. As you can see, VS Code is warning you about this Unicode character. Next, we need to define the function that will generate the data using Waterlily. For sim.flow, be sure to use the lowercase Greek letter sigma and not the lowercase ASCII character or the letter O. Also, be sure to use the lowercase Greek letter omega and not the lowercase ASCII character or the letter W. Okay, just one more step to go. All we have left to do is to write the code to generate the animation for the simulation. You can play around with the values for the duration and the step size to customize your animation. And that's it. Now all we need to do is hit Alt-Enter to execute this file. And then we can sit back and relax. The animation file will take a few minutes to generate, but the result will be an MP4 file that will be saved inside of your tutorial directory. If you didn't catch all of the code, no need to worry. You can find all of my code in my GitHub repository. You can play the animation inside of VS Code. Notice how chaotic the turbulence is at the very beginning. And then the vortex dissipates relatively quickly. But there's some lingering movement remaining, even up to the very end of this animation. Pretty cool, right? This wraps up the scientific computing series. We covered a lot of material, but scientific computing is a very large subject that continues to expand. There was no way that I could have covered the entire scientific computing universe in 13 episodes. But hopefully, this series provided you with a glimpse into what's currently available, and what's waiting for you somewhere out there on the horizon. I also hope that some of this material has inspired you when it comes to your own domain, whatever that may be. I certainly learned a lot, and I had a lot of fun learning it, and I hope you did as well. Before I go, I'd like to thank all of my channel members, whose generosity makes these videos possible. I'd also like to thank everyone who's donated to support the production of this educational content. And I'd like to thank all of you for watching, liking, sharing, and commenting. Without you, there wouldn't be a channel. As for me, I'll be taking a short break, but I'll be back in a few weeks with another fascinating 13-part series. See you then.